In this lesson, we're going to talk about standard deviation and variance. These are both measures of how spread out a random variable is likely to be. So, for example, if we know a value is exactly 1, there's no randomness at all, in which case the standard deviation and the variance would be 0. But if a random variable is a 1/2 chance of being 0 and a 1/2 chance of being a million, it's really spread out, right? So it's either going to be nothing or it's going to be really huge, possibly. So that would have a large variance. So the definition of a standard deviation is the standard deviation of a random variable x is written with a sigma x, and it equals the square root of the expected value of x minus its mean squared. So in this case, we're looking at sort of the distance between a random variable and its mean. So we take x and we subtract the expected value of x. In other words, we expect x to be this value, say, and x actually equals this value. And then that could be positive or negative, so we're going to square it. And we want to see how often that happens. So, in other words, how much do we expect this difference to be? When we square root it, we get the standard deviation. If we don't take the square root, we get the variance. Or in other words, the variance is the square of the standard deviation. So it's just liking the square root. And so, of course, that's sigma x squared. It's always a positive number because we're always squaring the number on the inside. So we're taking the expected value of a positive, which is positive. And the variance we'll see written as sigma squared sometimes, and sometimes we'll see it written as variance of x. So we're going to look at this, try to get an understanding by looking at this as a distance formula. So if you remember, the distance between 2 points, x1, y1, and x2, y2 from algebra is x1 minus x2 squared plus y1 minus y2 squared. And then you take the square root of that. And then in 3 dimensions, if we have a point x1, y1, z1, and x2, y2, z2, the distance is, you just take the difference of all the coordinates squared and square root it. So it's x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. And you could continue this for any number of coordinates. So if we had a random variable x, which was a discrete random variable, and had non-zero probability on the points a1, a2 through an, we can make an n-dimensional point that stores the values of x. So x is going to be a1, a2, a3 up to an. So this is just a tuple which represents the coordinates, or whose coordinates represent the values that x might be. And then we could also make another n-dimensional tuple of just expected value of x repeated over and over again. So this is just e of x, e of x, e of x n times. The distance between these 2 points on average, so now if we take the expected value of the distance of these 2 points, we're going to get the probability that x equals a1 times a1 minus e of x squared, plus so on, plus the probability that x equals an times an minus e of x squared. And then take the square root of that, and that gives you the standard deviation. So it is really, in a sense, a measure of the distance from the random variable to its expected value. And we're going to do one example using the distance formula itself. So as always, I like to do examples just to make sure it's clear, if it's not clear from just these abstract formulas, what's going on. So we're going to let x be a random variable with the probability x equals 2 is 0.8, and the probability x equals 5 is 0.2. So the set of values x could be is 2 and 5. And we can find the expected value of x using the usual formula. So we have 2 times 0.8 plus 5 times 0.2 is 2.6. So that's equal to our e of x. So we can make a 2-coordinate point with just the expected value in every coordinate. So 2.6, 2.6. Now we want to find the distance between 2, 5 and 2.6, 2.6. But we're going to weight the terms according to the probabilities. So with the weights, well, without the weights, it would look like the standard distance formula, right? So you take the square root of 2 minus 2.6 squared, so x1 minus x2, and then y1 minus y2 is 5 minus 2.6. But we're going to weight them. So this will be 2 minus 2.6 squared, but times 0.8, because that's the probability that x is 2. And then 5 minus 2.6 squared, but times 0.2, because that's the probability that x is 5. And that gets you the square root of 1.44 or 1.2. So the standard deviation of x is 1.2. A lot of times we'll work with the variance instead of the standard deviation. So instead of finding the actual distance, we just don't bother with the square root, as one way to kind of think of this. And part of the reason for that is the square root's a messy operator. So if we get a variance of 7, that's nice, we can kind of imagine 7, but it's a little annoying to have to take the square root of that. For one, you might need a calculator to do it pretty accurately, or you're going to have to do some work by hand to get several decimal places, and then it's going to be some decimal numbers, so maybe less meaningful. And both of the values will tell you just how spread out things are just as well, because they preserve order, right? So if a is bigger than b, then so square root of a is bigger than square root of b. So if something has variance 7 versus variance 5, we can compare that just as well as we can compare square root of 7 standard deviation to square root of 5 standard deviation. There's not really a good benefit in taking the square roots and making the numbers more complicated when we can compare the variances just as well. So the variance formula is the standard deviation formula without the square root. In other words, it's the expected value of x minus its mean squared. But if we do a little bit of algebra, we can rearrange it to another formula, which is often more convenient for doing computations. So here we're going to square the inside part first. So this inside square becomes x squared minus 2x e of x plus e of x squared. Then we're going to use linearity of expectation. So this becomes e of x squared minus e of 2x e of x plus e of x squared. And then we're going to use linearity again, but I wanted to make explicit that these e of x's inside are a constant. And if you watch the video on expectations, you remember that e of c of x is equal to c e of x. So a constant can come outside. And so we're just going to pull this e of x outside everywhere, and the 2. So e of x squared minus 2 e of x times e of x plus, and then the expected value of a constant is the constant, so e of x squared. And then this is minus 2 of x squared here, and plus e of x squared here, so one just cancels. And we get this, which is hard to say in a clear way. But the variance of x is e of x squared minus the quantity of e of x squared. So it sounds like when you read it, e of x squared minus e of x squared. And that's a little unfortunate because a lot of people think this is always just going to be 0. But it isn't 0. In fact, it turns out that e of x with a square on the inside has to be bigger than or equal to e of x with the square on the outside, because we just showed that the variance equals this thing, and we know that the variance is always bigger than or equal to 0. So let's use this to compute. We'll compute this standard deviation again, but now using this other formula that we have found. So if we square the random variable x, we get the probability that x squared equals 4 is 0.8, and the probability that x squared equals 25 is 0.2. So we can find e of x, which we've done before, and that's 2.6. And we can also find e of x squared, which is now 4 times 0.8 plus 25 times 0.2, which ends up being 8.2. So now we're going to plug these values into this formula. So we're going to take e of x squared minus the quantity of e of x squared, which is 8.2 minus 2.6 squared, which is 1.44. So we get a variance of 1.44 using either formula. And if we take the standard deviation, that just means to take the square root, and we get 1.2, which is what we ended up computing above.